I'll first introduce myself briefly. So I'm David Cohn. I'm heading up the new engineering education team here at Timescale. Um, and this is something that we're doing. So the team is sort of responsible for doing education both for engineers at Timescale, and we're going to be doing some of this stuff for the outside world. And so a lot of the stuff that we're building for internal folks, like we hire engineers who have lots of different backgrounds. They're working on and they're expert in a specific part of the platform, but maybe not. They're not an expert in databases, don't know as much about what Timescale is or how Postgres and Timescale work. And so this course was something that we wanted to start off with, just to sort of help them learn a bit about what our product is so they can understand our users better, et cetera, et cetera. It's meant for people who have some background or who have none. I'm hoping we're starting pretty sort of at the beginning, and we'll go over some more of this in a minute. I've asked Miranda, and you can introduce yourself, please, in a moment, to come and sort of act as an audience proxy and help ask questions. So if you have questions, please do put them in the chat. Miranda, do you want to introduce yourself quickly?
Yeah. Hello, everyone. My name is Miranda, as David said. I'm a developer advocate at Timescale, and I'm super excited for this course and just all of the stuff that's coming out of the knowledge department, because, I mean, who doesn't want to learn more? One, and it's more about databases and Postgres, so that's super fun. And later on, Timescale as well. So lots of awesome stuff that I'm very excited about to learn. And so definitely ask questions. We love questions. Do not be afraid, because I love asking crazy questions. Also, I apologize that the sun is hardcore, like right in my face. So
yeah, that's beginning to happen to me too. So we'll see how the lighting goes.
Yeah, the sun doesn't shine all day in Pennsylvania, and then right now, of course, right when we stream, is whenever it's like,
that's
oh,
how that always is. So the answer is, I think we just need to stream more, right? Then you'll have better weather.
Yeah, exactly. Awesome.
Cool. So yeah, so I am actually, can we take this? Let's take this writing off. Okay. So welcome. So this is your exercise that I was giving you. I hope you've had a little bit of time to think about what maybe this is. So we'll start with a little bit of background. So this is a patent that's actually for something that is involved in the process by which we make a lot of fertilizer, so that it helps us feed the world. It's also how we make bombs. So some background on this is that in the early 20th century and the late 19th century, there were these islands off the coast of Peru. And where we got our fertilizer was actually because there were these islands. They had hundreds of thousands, millions of birds that would flock to these islands over many centuries or millennia. And of course, birds, when they gather in a place, they make a lot of bird shit. Excuse me, poop. I don't know. I guess this doesn't need to be
I need like
family friendly.
like a beeper sensor.
Yeah. So these birds would poop on these islands, and that poop would build up, and this is how we got our fertilizer. They would send boats down to these Chincha Islands, and they would actually just like shovel bird poop into the boats. They would take that back, and that was one of the main sources of fertilizer for the world. It was a similar process to get the nitrates that we needed for bombs, though mostly in the Atacama Desert and other places, until the early 20th century, when the Haber-Bosch process was developed. And this process is a relatively simple chemical reaction in which you take nitrogen and hydrogen and you make ammonia. And that ammonia can then be transformed into nitrates and all sorts of other stuff very easily. But so if it's this simple reaction, like, why didn't someone come up with this sooner? Well, the real answer is that it's not exactly a conditions that exist on Earth all that frequently. So it's at 100 or 200 atmospheres of pressure, so very high pressure process, and a rather high temperature, 500 to 600 degrees Celsius. that you need to have in order for this to happen. You also need some catalysts to make it work at any reasonable yield. But this was really the first high pressure process. No one had ever worked with these types of pressures. I mean, high temperature was definitely a thing that had happened, but high pressures, that was something that really was new, it was novel. They hadn't even really done it at lab scale ever. And so when Bosch was the one who started scaling up this process. When he started to scale it up, he developed a pressure vessel. So you can now see that this was an apparatus for working with hydrogen under pressure. That's what this was. That's a little citation of the patent. You can see some of the pressure valves on the top. But there's a bit more to it than that. So first off, he needs to contain these pressures. So he needs to work with steel. And the Bessemer process had been relatively recently developed. So they can get high pressure steel that can really, or high grade steel, I should say, that can withstand these types of pressures, which was something that you couldn't really do before. So that's one big thing. And so they do that. They make this nice hydrogen vessel. And they start it working. They actually encase it in concrete because they're a little worried that it's going to explode. It doesn't explode. However, it only lasts 3 days. And in 3 days, after 3 days, it just breaks. It doesn't explode, but it does just sort of like fail. It basically comes open, it comes apart. So, and the reason for that, they sort of figured out after a while, is that, well, hydrogen is tiny, like really tiny. And so you have it in this pressure vessel, and as it's in the pressure vessel, it actually starts diffusing into the steel around the outsides. And so you get something called hydrogen embrittlement. So the steel actually gets embrittled, it starts to fail. All of its nice properties around being able to contain that pressure, all of that stuff, all of the strength that they were paying a lot of money for, just goes away after being exposed to high pressure hydrogen. So they figure that out, and then they try and solve it. So how would you solve it? Well, your answer might be, well, I try to find some steel or something that I could add to the steel or something that I could coat the steel with to try and make it resist the hydrogen embrittlement somehow. And so they did that, and they had a lab where they were working on all of these things. This is actually, I think, a picture of the lab where they were doing some of this early hydrogen research. And so they're trying to find something that would not be embrittled at these pressures, some sort of coating. They tried coating the steel with gold. That was dumb for cost reasons, right? But hey, maybe if it worked, you might be able to amortize it because this was a really important process. None of it worked. They spent 6 months trying to figure that out. And so Bosch, by the way, is the founder of BASF, right? So if you notice, this is a BASF historical pamphlet, right? They're a huge chemical company. They're one of the larger companies in the world, certainly around this type of stuff, I think still. So Bosch has a scientist working on this for 6 months. And finally, he's out for a beer because all the good ideas come to you while you're out for a beer with some of the engineers. And he realizes that really what he needs to do is reframe the question. Instead of asking, how can I prevent the hydrogen from embrittling my steel? He said, well, what if I did this other way? What if I let the hydrogen embrittle my steel, but not all of it? What if I made a sacrificial layer? And so what he does is he takes a very cheap iron that doesn't contain carbon, and he puts it on the inside. You can see this layer here. And that layer is going to be there to basically get embrittled. You're going to allow the hydrogen in. And in a few months, when it wears out, you get rid of it. And you have the steel on the outside, and that's going to hold the iron in place. But it doesn't, it's just there to hold the iron in place. The iron is there. And that's not going to wear out because the hydrogen that it's encountering is not going to be at high pressure. Okay, so that is sort of the first step in this really cool solution. But then he realizes that he can also just decouple the functionality. Now that this steel is here, he doesn't need to have it contain gas. Because one of the big problems that he realized is, well, okay, if I have this layer of iron and then I have this layer of steel and there's a gap inside and the hydrogen's diffusing through the iron, then it's going to get caught in a little layer between the steel and the iron. And if the hydrogen gets caught there and it builds up, then it could explode, and that would be really bad. So at first he's trying all these different things, and then he realizes, well, wait, now that this steel is here, I don't actually need it to hold gas in at all. And so he drills holes in it. And this is the thing that I think is so brilliant. All he does is he drills some like pencil-sized holes in the steel. Because it can still hold the iron in, it can't hold gas in, and in fact that's the point, right? It doesn't hold gas in now. Now the hydrogen that diffuses through can just escape, and in the big plant, it's going to be more than diluted enough that it's not going to explode or anything like that. So these Bosch holes are really, really smart, I think, innovation in terms of engineering. So why the heck am I telling you about this when we're starting a course about the foundations of Postgres and TimescaleDB?
Why
That I guess is the question that may be on your mind. Why did I just explain Bosch holes? Well, the first reason is that it's my favorite engineering story. It's just like something really lovely that I think is really cool. And it's my course, so I get to do that if I want to. And then, so then the next thing is that I learned about it in one of my favorite books. So this is The Alchemy of Air by Thomas Hager. It's a lovely story about all of this. It's incredibly well written. And one of the things that I think is that, we're living in a world where it's very important for engineers to know how to write well and to convey ideas in a succinct way that people can understand. And I think that science writing is a great way to learn about that, because science writers often have to do that, and science history writers often have to do that. And I think that this is a good example of that. So, I would suggest getting this book and reading it if you're interested in any of that stuff. But moving on to some serious reasons. So the thing that I wanted to sort of show here is that context leads to understanding. So when I showed this to you the first time, right, you had no idea what the heck it was. And it just sort of looked like a weird drawing that you couldn't quite tell all the different things. And now you know basically what all these different parts do. Still not sure what this bit does. I think that may be where the catalyst is contained. Not 100% sure. But you know what some of these layers are. You can understand how this thing works now that you have an idea of what it's trying to do and some of the context in which it was built. And it also is sort of an analogy for the type of internals knowledge that I'm trying to build around Postgres, right? So as we get some more understanding of this, like you could not design a Haber-Bosch reactor from the level of understanding that I'm giving you. You could not work on one, right? There's a lot of other things that you would need to know. However, you might be able to, understand as the HVAC person in the plant that, hey, I need to make sure there's enough airflow over this thing so the hydrogen actually does get to go away. Or I need to, not block these holes, which are serving a really important purpose, right? You have enough of an understanding that you can understand it in its context and how it relates to other things. So if, within Timescale, that might be someone who's working on another part of a database, like you can understand the whole at a high level, so you can better work on the parts. Or even a user, right? Someone who's trying to use Timescale, right? You may have to get a deeper understanding of a particular part of Timescale for your project, or maybe the high level understanding is enough. But you'll also just know all of these things that exist and a little bit of how they work and why we made some of the choices we made. So, this might be enough. Like it's the type of information, if I can analogize it to for those of you who have used Postgres a bit, right? It's enough information to read an explain plan, but not enough information to be able to like go and hack at the planner. So if you don't understand it, that's fine. That's some of the stuff that we're going to get to in this course. But just for those of you who are coming from that type of background. So getting into the actual course, what's a database? Well, for me, I like the Wikipedia explanation, right? It's an organized collection of data stored electronically. And so maybe importantly here, there's also something called a database management system. So something like Timescale or Postgres is actually technically a database management system. which is the thing that allows a user to interact with the database. The database is the software maybe plus the data, right? The data plus the data model, sort of how it's organized, et cetera. And the database management system helps define that organization, helps the user interact with it. This is one of the things that I run into when I'm trying to explain to people, well, what is Timescale? Where do you work? To someone who doesn't understand it, they say, well, I work on time series databases. Okay, well, what kind of data do you have? Well, we don't really have data. We just work on the software that allows you to store the data, right? So that's just one thing that I wanted to point out. Oh, I just said those things. And often they provide some sort of guarantees around transactionality, ACID, multi-version concurrency control. We'll define some of these in a minute, and we'll do some more in future lessons. So let's go over what we're going to do today. I want to start off with some background, especially around memory and storage, as we start sort of on our journey to understand a lot more about databases, et cetera. We're going to do a little bit of history and context. We'll get into some more of that in the next lesson, I think. And then we'll talk about ACID guarantees, which again, we'll define if you don't know what they are now. And then we'll talk just a little bit about indexes, keys and indexes, and how we can search for things fast. And then I'd love to spend a little bit of time just asking y'all to put in the chat sort of some of the things that you'd like to cover in future lessons, if there are things that are particularly interesting to you. I think that would be a great time for you to just put those down, and we'll start gathering them. If you're watching this later, please do put it in the chat. And if this is in a year and the course is already done, I can't necessarily work it into this course, but we will take a look at it and hopefully work it in at some point. So some background, and these are things that my background actually is in electrochemistry. Part of the reason that I know about this stuff is that I studied some chemical engineering, right? So when I took a little bit of some computer science stuff in school. But then I sort of made a switch over to databases when I was at a battery manufacturing company, and we needed to store our data somewhere. And so as I was learning this stuff, I gleaned some of this stuff as I was going, and had to pick it up from context and other sorts of things. And so these are some things that I sort of wish I knew and wish I understood a bit better as I was getting started, and wish there had been some place for. So I'm hoping to provide some of that here. Please stop me, or please put a question in the chat. Miranda will, jump in and ask me things as she sees fit, or if especially she's getting some audience questions around something, she'll definitely stop and ask. So very high level computer architecture here. You have data, it goes into the central processing unit, which performs some operation on it, and then you output the data. Cool. So really, really high level understanding of what a computer is, right? So that logic operation, right? So basically say you have 2 and you want to square it. Okay, so the input is probably 2, and the fact that you want to square it, the operation you want to perform. The operations is the squaring. It performs that feat of intelligence, which seems like not much, but you can get a lot more complex than that. And then it's going to output. It's going to put the result for somewhere else, right? So it says here's some things that I'm going to work on, and then I'm going to put the output somewhere and tell you where that is. And so where that data goes is usually either into memory or to storage. And so what are the differences between memory and storage? This is something that we need to know for databases, and because a lot of what they do has to do with how things are stored in memory or on disk, and that's an important distinction. So in general, the differences are here. And by the way, I will say that some of this is changing now. Like some things are happening that are a little bit weird in terms of the storage market, and storage becoming a lot faster and maybe more durable, etc., or memory becoming more durable, and the lines are blurring between memory and storage a little bit more right now. But this was definitely true when Postgres was developed in the early 90s, and certainly true when even more true in some ways when people started developing databases in the 60s and 70s and 80s. So going over this, I think that people know what relatively expensive and relatively cheap mean. I'm not going to go into that too much. So what's volatile and durable? And no, it does not have to do with the kind of mask you have to wear while using it. Right? This is, I don't know. Do people have masks for volatile organic compounds? Maybe, I don't know. Whatever, it doesn't matter. I can never tell when
That's
I'm
from
doing
your
these
chemical
things.
engineering background.
Yeah,
Most
yeah,
people don't
maybe.
deal with masking.
I mean, if you've painted, you might have to do it, or like if you're sanding,
True.
there's reasons that you might need these masks. Come on. Anyway, uh, poor jokes, my specialty. Um, anyway, so let's talk about what the difference between volatile and non-volatile, or volatile and durable storage. Um, so something that is volatile, basically, it means it needs power in order to maintain the data. So durable storage will keep the data even when the power is off, but memory or volatile storage won't. That's the basic gist there. Obviously, that has a lot to do with what we're doing in a database. But the other part of this is that memory is usually, and volatile storage generally, is often much faster than storage, or than durable storage. So you sort of pay the price of having something that is safe when the power goes off, um, versus it being slower. So when we say slower or faster, what do we mean here? Well, there are a few different things that we might mean as we're defining these things. One measurement that we might talk about is latency, which is the time that it takes to get to the first response. So you might have a very large piece of data or something that you're fetching. Latency really is talking about how long it takes to get that first thing, just the beginning of it. And then throughput, though, talks about how fast can you push stuff through. So if I have a really big file, I can read it all really quickly. I can push it through the pipe, in essence, faster. So that's often measured in megabits or bytes. I never depends. Multiply by 8 or divide, depending, um, or gigabytes per second. Um, and then one that's often talked about a lot, and it's IOPS, or input output operations per second. Um, yeah, actually, I don't know whether the O is for input output, or for input output operations. I don't know. So this is for random blocks. So let's talk about what that means. So seek time, right? So we're for IOPS, we're adding up the seek time and the latency, and that's for random blocks. So it has to do with basically, when we talk about seek time, we're thinking about something like a spinning disk, which means that on this spinning disk over here, you can actually see there's this like little magnetic head, and you have this part of the disk that spins. And so when you want to read a part of the disk, you have to move this head, and the disk has to spin around. So if you're reading things in sort of random locations across the disk, then you have to wait for the disk to spin around to the right place and the head to move in order to get the data that you need. Now, things are very fast now these days, especially. They weren't necessarily when these things were first developed, but they're pretty fast these days. And the blocks are very small. When we talk about a block, I don't know whether I mentioned this. We'll talk about it in a minute, just in case we don't. But so not everything's a spinning disk, right? There are different types of things that we can talk about here, right? So we can talk about um, uh, memory, or RAM, which is random access memory. There are other names for that, but you don't see too many of them. So that's sort of the volatile stuff for the most part. Then we talked about already the storage, or spinning disk, or hard drive, or disk drive. There are also these new things that we're talking about, right? Like SSDs, solid state drives, or flash drives, or non-volatile memory express NVMe drives, is what you'll usually hear them called. And then there's also something like tape, which was much more common um, earlier in computing's history, though it's certainly still around, right? And tape is basically exactly what it looks like if you're old enough to remember a VHS or cassette tapes, right? It was magnetic tape, and you would have to wind it. So when you're talking about IOPS, right, tape tends to have pretty good throughput. Once you get to the right place, you can read things off of it pretty quickly. But in terms of IOPS, it's very low because you actually have to rewind the dang thing or wind it to get to the place where you have something stored.
The
You
number of
also,
hours spent winding
yeah,
VHS tapes, man.
yes, yeah. So everyone knows, right, that it can take a little while to get to the information that you want on a VHS tape or a cassette tape, or anyone who's used them anyway. Right. So that process, right? It was very important to just understand and how that sort of seeking process would work. And this also has to do with random versus sequential I/O, input output, right? Um, so this deals with where blocks are located relative to each other on disk. So if you have sequential blocks, then you can read them pretty quickly. But if you have random blocks, like on that tape, that would be very slow. And random just means it's all over the place. And one of the key things just to note, because it's something that comes up in databases all the time, and there are a lot of design decisions that are made to deal with this, like uh, type of IO type, right? Is that sequential is almost always faster than random, especially on older drives. So like when a lot of these technologies were developed, that was a very key design constraint. Um, but uh, it tends to still be true even today. So, and by the way, just to again, some of this is meant to also be some reference material for y'all. I will make these slides available. So, like, if you're confused and you're going back, this is someplace you might want to look. Right. So, what's a block? A block is the smallest contiguous data size that you can ask your disk to fetch. So, it's basically how we divide that disk into something that is addressable, right? You might only want a few bytes of information, but storing like where those few bytes are like live will soon become as big as the bytes themselves self selves. So it just doesn't make sense. So you have to say, well, I need like a smaller reference area, so I can point back to the right thing. You'll also hear them called pages. Usually a page is in the file system, whereas a block is on the disk. We'll use them for the most part interchangeably here. So I am going to try and identify some terms that are sort of basically the same thing with slightly different or different names where they're used somewhat interchangeably, because those are always confusing as all get out. So I'm going to try and identify those. If you find one that I'm missing, or if there's another name that you've heard used for something, please let me know. That would be very helpful as well. So what you can think about really in this, as we go back to our high level computer architecture definition here, um, uh, you can think about sort of this is really moving between storage and memory, right? So memory, usually you read something from storage into memory in an operation, and then you're going to access it in memory, do some stuff with it, and then maybe write something back to storage. And that's usually how things are designed. So you work in memory, and then you write or like do more uh, uh, long-term operations to storage. So, and this is certainly also what happens as you boot up a computer. For instance, you read from storage into memory for the first program that a computer is going to run, and then it stays in memory, and that's what it's going to run for a while, and it moves other things in and out depending on what it's doing. So now we've got some background around how computers work. So why were databases originally designed? So in the 1960s and 70s, computers are relatively new, trying to figure out how to use them more effectively, and they're being used in a number of different uh, places. So this was like before the word database was a word, really, right? So like it was beginning to become a word, but like people would call it a database with two words, or a data bank, or things like that. The OED, which I found on a blog, I should probably find access to OED at some point, right? Says, well, actually, that at least there's uh, some apocryphal background, that it was actually coined by workers in military information systems, where it's like, okay, well, a fighter base has fighters, so a database has data, right? So that kind of makes sense. But you can note in that definition, but in that entry there, that there were a number of different um, uh, a number of different users of databases, you might say. So military information systems for doing logistics, for planning purposes, etc. There was scientific users for keeping their data, or for, of course, counting citations, because if you're a scientist, what do you use a database for? Well, for counting how many times your papers have gotten cited, at least if you're in academics.
The only
And
reason to use databases in science.
of course, of course. Um, and of course, businesses, banks. The classic example that are used in a lot of the database papers is like parts and bills of material. So like, this is all the things that make up X that we need to ship, and this is where they come from, and whatever else. But in general, right, you have shared data between multiple users, and so it needs to be reliable and predictable to access and to store. And that's where we get to something like ACID guarantees. So these guarantees, so what ACID stands for, by the way, is atomic, consistent, isolated, and durable. The names and descriptions of these things, though, were really provided later than the original implementation. So systems started doing this, and then people later said, well, oh, these are important, let's describe them. And so the name ACID guarantees sort of came after a lot of these will be really being provided by commercial systems. So to understand this, let's start with a scenario. And the scenario is, okay, Amy with account number 200.
I love scenarios. Let's do this.
Wrote a check to Barbara, who has account number 300, for $75. So what we need to do really is debit $75 from account 200 and credit $75 to account 300. So let's go through these sort of in order of what I think is easiest to understand, especially given our background with storage, right? So whatever happens, once we have gotten acknowledgement from the database system, so once it is said, yes, I have this data, you need to know that it's actually written to non-volatile storage, which means it's crash safe, which means that like if I go away and the database happens to crash right after, and then it comes back up and I ask it again, if it said it was written, it'll still be written, because otherwise I'd have to keep all of that information like in the memory of my application, or store it separately in the application so that I could replay to the database if I needed to, if the database happened to crash. So the database has to manage that itself. So that's the durability part of this. So it has a lot to do with like written to durable storage. Cool. Atomic. So this, again, it involves this acknowledgement, which says like the database has to say, hey, I got it. Hey, something happened. It has to tell you that as the client or the user, hey, this did in fact happen. But it says that once the database sends that acknowledgement, it means that either all of what I did happened or none of it. So the database might also say, hey, error, rather than acknowledgement. It might say error, this didn't work for whatever reason. So this is like the idea of transactionality. You have a commit or a rollback. And the important reason for this, right, is that either we want both Amy's account to be debited 75 and Barbara's account to be credited 75, because otherwise Amy will get, if you debit Amy's account and don't send it to Barbara, Amy's going to get pretty mad. Barbara's also probably going to get pretty mad, right? Everyone's going to be mad at you. And I suppose if you credited Barbara's account and didn't debit Amy's account, both of them would be very happy, potentially, but your bank would go out of business very quickly. So we really need both of these things to happen, or neither. We don't want only one. So that's the idea of a transaction, or this atomicity guarantee, which is to say, hey, it's either all or nothing. Cool. So then consistency, consistent. So this is one that gets a little bit harder to understand. It's like a little bit wishy-washy to an extent. But it's basically saying the database has to move from one valid state to another. So this might mean a few different things. It might mean, we can't put in junk data. So if a teller enters into our, check system 7F5 instead of 75, like we just reject that because it's not a valid, floating point number or money type or whatever. However we're parsing this, we know that that's not a real number. Okay. So we might also have triggers or constraints that say, hey, the balance can't be below 0 after a debit. So Barbara's account can't if she had $74, it wouldn't work. But if she had 76, it would. And she had 75, it should work too. So atomicity is intertwined here, right? So if we want to fail that whole transaction, right? If something like this, if we fail a consistency check. And then isolation. So the idea of isolation essentially is that multiple concurrent users who are modifying the database at the same time are the same as if they had done so in some sequence. And this, again, is the one that gets a little bit harder to understand. So let's look at a scenario. So let's say another teller is entering into our bank processing software that we have written using our database, a check from Amy, again, with account 200 to Carol for $150. And they're entering into the system at the same time of our first transaction where Amy was sending Barbara $75. So after both transactions, Amy's account balance should be debited by $225. Right? So the first thing that we definitely don't want to happen is they both, so like, let's say, she had $300 in there to start. We don't want them to both say, hey, okay, we're starting with 300. I want the new value to be 300 minus 75 or 300 minus 150. Because then it's as if one of the debits didn't occur, right? So she would only be debited by either 75 or 150, whichever happened first, whichever happened to happen first. Like if they're both trying to access at the same time, they could read, hey, 300, and then write, okay, well, 150 minus or 300 minus 150. Well, that's 150, but like she should end up with $75 in her account if we start off with 300. Okay. We also want to make sure, for instance, that our consistency guarantees are run, right? And that if we were to go below 0 on either of these things, that it wouldn't work, or whichever transaction takes it below 0 stops working. Now the ordering is not necessarily defined. So if the $75 one happens to get there first, then that will work. So usually when we're doing this, we deal with this in a few different ways. So we can do locking. So that's basically saying, like, I'm going to say this record is I'm modifying this record. You can't read it until I'm done. And so you can't read it or write it right until I'm done. And then we also use snapshotting or multi-version concurrency control, which keeps a copy of the old records around, and from when I started, and then at least until I've finished. So then other readers potentially can still be working on a consistent state even while I'm updating the database. So usually databases use some combination of locking and multi-version concurrency control to achieve what they want to achieve. So why not just locking? Well, in general, if we only lock, we end up with like long wait times. Especially with read locks, we can limit concurrency pretty significantly. So the sort of state that we might end up in here, right? Imagine that we have a reconciliation process that is just making sure it's reading all the records, making sure they add up, or doing some things around all of the record in time. Well, you want it to read, say, Amy's account. Then the transaction happens where Amy's account is updated and Barbara's account is updated, and that happens at the same time. But this other reconciliation process has already read Amy's account. So Amy's account has $300 in it to start, and then Barbara's account has, an extra $75. So that $75 would seem to just appear if the reconciliation process happened to read at exactly the wrong time. It's sort of one part transaction happens and another part of it after a transaction happens. So you want to get a consistent snapshot, which means you may want to get a consistent snapshot, which would give you a consistent view of the data as if you were doing your whole thing before, say, Amy's that teller's transaction completed, or after, depending. But you just need a consistent way to see it. So anything that happens in the meantime while you doesn't affect your reads. So it allows you to get out this. So usually we use locking to deal with writes that are happening at the same time, whereas we use multi-version concurrent control to deal with reads and writes that are happening at the same time. Cool? Questions? Otherwise, I will move on. So, so once we've gotten there, we're like, okay, well, we're looking at this scenario, right? And we're thinking, okay, so I need to access these two accounts, and I want to do that relatively quickly, right? I need to get to account 200 and account 300 and perform these two operations relatively quickly. So I'm not like locking them up while I'm waiting to find the other one. And then like there's another person who's waiting to update some records, right? Like, so one of the big questions that happens in these early database systems is, how do we find records quickly? So when I think about that in terms of my book here, right? When I was looking for that story about Bosch holes, right? I didn't go and just like try to reread the book very quickly. I'm sometimes a relatively fast read. I would have, that would have been still pretty darn slow. And I have my things here, but now I'm holding things up and I can't advance slides, right? So no, what I did is I looked in the index, right? And so what I basically do is I have a different way of organizing some of the information in the book. I looked up hydrogen in the index, and it told me the pages that that story lived on. I had to look a couple times. And we developed indexes for these types of databases as well. So the main goal of an index, right? Usually we use something called a B-tree index. This was developed around 1970. They're basically made to find items on disk quickly. It's a generalization of a binary search tree. For those who have some more computer background, we'll show a little bit about how this works, and we'll get into more of that later. But it's generally a very efficient way for organizing data on disk so that we can minimize those random reads. And so basically, it's a tree structure that looks something like this, where you have a few items telling you, okay, so in that top row here, we see 32 and 67. So this is sort of the first node in our B tree, and you'll notice that there are these dots. So these dots, in our case, are going to define some pointers. They say this is where the next stuff lives, or where the stuff with this information lives. And basically, we say, look, everything below 32 lives over here. Everything between 32 and 67 lives over here, and everything above 67 lives over here. And so we can keep going down the levels of a tree like this, and they're going to the next stuff. Eventually, we'll get to a leaf page, and depending on the type of B tree that you're using, the data will actually be stored inside of that leaf page. So we see as we traverse this tree, we say, if I'm looking for 6, right? Okay, so it's less than 32 is my decision point here. And I shouldn't click. That's showing it's less than 2 is my decision point here, and then it's between 5 and 10, and then okay, I found the data, right? I can follow these pointers sort of to find them. It also has some other nice characteristics where usually in a lot of sort of database type applications, and this came a little bit later, you often have pointers between your data so that you can scan it in an ordered fashion as well. So each sort of leaf page, and these are called leaf pages down here, will point to the next leaf page. So, if you're something like Postgres, and we'll get to this again more, you can do an index-only scan. That's what we're doing. We're actually scanning these leaf pages. Why wouldn't we just start in a sorted list? Well, when we're looking at this type of data, you'll see that it actually takes more random operations to just do like a binary search on a sorted list. It also makes it very hard to insert new data into it, because in order to do binary search on that list, you sort of need, you can't really use the linked list. You kind of could, but it would be very hard because then you couldn't do binary search very easily because you don't know where anything is. You don't know where that midpoint is, which you need for a binary search. Binary search just means we're going to take the thing, split it in half. It's sort of what you do actually when you're looking in the index of a book. You say, well, what's here? Well, okay, I'm going to try to see where I am, and then I'm going to go, well, another couple pages to see sort of what that letter is, and eventually you find the right letter that you're looking for. So it's a standard way of looking through an ordered list. So But it ends up involving a lot more random disk access is the basic reason, and then it's hard to insert things. Anyway, we're going to end our lesson here. And oh, it's not February 1st anymore. It's February 10th now. I did this initially for an internal audience on February 1st. We're going to do these just sort of a little bit later for y'all, and we'll just keep doing this hopefully every couple weeks or so. We're going to end the lesson here, but basically what I wanted to what I think I've laid out, and hopefully y'all agree, and hopefully people have some questions or other things, is that I want to have laid out sort of where we are in the development of databases. So we have some things that businesses are using to store data. They have some of these guarantees. They have some of these ways of searching quickly for some of the data. And we're beginning to get to the point where we can get to the relational model, which is really foundational to Postgres and Timescale, which is built on top of Postgres. So that's what we're going to start covering next time. And we're going to get into a bit of hopefully some Postgres architecture, depending on sort of how long the relational model stuff takes, and how that works, and how we actually do a little bit of databasing. So with that, we have a bit of time left, though. So the sort of question that I have is, what do you all want to cover? Are there things, as you're seeing, that would be useful for you? Was this like a good overview, etc.? I think maybe now that I'm through my presentation, we can also switch back.
Yeah,
that's
we can do this.
Yeah, sure, that's fine. Here. Lovely. So I don't know if there are any questions in the chat.
We didn't get any questions, but does anyone have any questions at this point, now that we kind of hit the end of the lesson?
Or anything that you would like us to cover in the future, if there's anything in particular that you think would be helpful. Like I said, this lesson is really meant to be a background. It's part of why I called it lesson 0 rather than lesson 1. It's not just because we computers like to index things from 0, even though Postgres doesn't do that, which is annoying. But yeah, so hopefully it's sort of a prelude and some background information that might be useful for folks.
Yeah, and if there also were topics that you maybe want more information on, like potentially, like if you feel like it'd be helpful to learn more about like the acid stuff, or anything like that.
Yeah, I think we will go more into indexing when we sort of come to that. I think that's a thing that I wanted to provide a basic overview of some of how it worked, just to sort of begin to show people some of the stuff that's involved. We will get to like a more in-depth description of some of that, especially as you get into Postgres, and I've laid some of the foundations there, and talk a little bit more about how indexes in Postgres work. We may also talk about some indexes that aren't B trees. There are some other types that Postgres allows you to use. So those are sort of some of the things that certainly we will get into. But yeah, if you want to know more about whatever, please do let me know.
Yeah, we want to hear from you all. Yeah, this was awesome. I super appreciate, even whenever you gave this internally. I know that I learned a lot, and like the history behind things. I think it's really cool to learn about the like history on how things kind of came to be, because I feel like it just gives me more like brain context and to like remember things, but also I don't know, it's always fun to learn about like how things develop. So I
yeah,
love
I
that
mean,
you added
for me, I think it's really important to, like, in order to actually understand things, my basic theory is you kind of need to know a little bit about how the people who developed them were thinking, and like what were the problems that they were trying to solve.
Yeah, totally.
Because otherwise it can be really hard to get any context. Like, why did they make this choice? Why this is so weird? What's going on? Like, there's usually some history to that. There's usually some reason. Now, this is not to say that it's perfect by any means. Like, there may well be things that don't work right and that we need to throw out in a new context, and that's totally reasonable. And if this sparks ideas about things that maybe we should try to figure out how to work around or do differently or else, like, awesome. whether you're within Timescale or otherwise, please feel free to, give us ideas. So, that's totally fine. Things do change, but I think that understanding some of the reasons behind them can be really important for understanding how things work and putting them in context.
Yeah.
We're excited to be doing this, and let us know what you think and anything we can improve on as well. So,
yeah, awesome.
Thank you all.
Thanks, everyone. Have a great rest of your day, or evening, or morning, or night, or anytime. Bye, folks.